All right, guys, so this video is going to cover notes 8.1. This will be going over similar right triangles, otherwise known as geometric mean. So before we start going into the notes, we just want to review some important concepts here. The very first thing we're going to look at is the parts of a right triangle. Okay, so super important for this chapter. The parts that we're looking at for a right triangle, the very first thing that we want to look at is something known as the hypotenuse. All right. Your hypotenuse is always going to be located across the 90-degree angle, and your hypotenuse represents the longest side of that right triangle. Okay. And the hypotenuse only exists in right triangles, right? We know that this is a right triangle because we see that angle C has a little box right there indicating 90 degrees. Okay. So to summarize, your hypotenuse is across the 90 degrees, and the other side lengths of your right triangle are known as your legs. All right. And so we also want to take a look at reviewing what we learned in chapter 7. Remember that when we're looking at similar triangles, corresponding angles are congruent, right? And so what this means is if we have two similar triangles, then the corresponding angles are congruent. So if we were to take a look at some examples here, right? Let's look at this blue angle right here labeled as X, right? If I was to say that that's 40, then it would have to be 40 in the second triangle if those are similar. The green angle, let's say this one is 80. Well, if that's 80, then this is 80 in the second triangle. And then lastly, let's say that angle Z, the red angle, is 60 degrees. Then this would be 60 degrees here as well. So the idea here is that if you have two similar triangles, the corresponding angles must be congruent. So in this first triangle, if I have a 40 degree, 80 degree, 60 degree angle, I better have a 40, 80, 60 degree angle in the second triangle. And next, it's also noted that if we have two similar triangles, then the corresponding sides are proportional, right? And what this looks like is what we have down here. Okay, proportional is whenever we would set up basically two ratios or two fractions and cross multiply to solve for missing side lengths. And we'll see kind of how that pops up in some of the problems that we look at today. And so one of the newer concepts that we do want to talk about now is something known as geometric mean. So the geometric mean of two positive numbers a and b is the positive number x that satisfies this proportion, right? So geometric mean really is this proportion here. A over x is equal to x over b, right? Or in short, might be worth noting here that your shortcut for geometric mean is literally just this equation, x squared is equal to a times b, all right? But this proportion for geometric mean that we have popping up here is going to be something that you're going to see pop up throughout the notes. So like what we have here in this a over x is equal to x over b, a common theme you're going to see in the problems that we look at today. But for right now, let's look at an example that asks you to find the geometric mean. So example 1 says find the geometric mean of 4 and 12, right? In this case, when they ask me for the geometric mean, it's understood that I'm using this formula, x squared is equal to a times b, right? And you might be wondering right now, well, what is A and B? Well, A and B represent the numbers that they're asking you to take the geometric mean of. So this formula, x squared is equal to AB, is going to turn into x squared is equal to, well, A is 4, so 4 times B is 12. And if we keep going here, then we get x squared is equal to 4 times 12 is 48. And if we want to go ahead and solve an equation that has an x squared, then it's important to note that the way that we cancel out a squared is by doing the opposite. The opposite of squaring would be to square root. So square rooting both sides will cancel out the exponent of 2, leaving you with x is equal to the square root of 48. And like we saw in the notes for 8.0, or simplifying radical notes, we can simplify the 48. 48 can be broken down into 2 times 24, 2's prime. 24 can be broken down into 2 and 12, 2's prime. Here we can do 3 and 4. Let me scroll down here. 3 is prime, and 4 can be broken down into 2 and 2. Right, so if we were to simplify this radical, then what we're doing now is we're replacing it with all the numbers at the end of our branches that are prime. So 2 times 2 times 3 times 2 times 2. Right, and so remember that this works in pairs, right? I have a pair of 2's here. That means that one 2 is going to come out. I have a pair of another 2 here. So that means the second 2 is going to come out. And then all we have left over under the square root is a 3, right? And so all that's left for us to do here is put our x equals out in front and just multiply the 2's that we have on the outside. So this gives us 2 times 2 is 4. So x here will be equal to 4 times the square root of 3. Right? And so you'll realize that sometimes we are going to get answers that pop up as a square root. The expectation moving on now is going to be that you simplify those square roots or those radicals whenever possible. Okay? So that's just an example looking at geometric mean, right? Let's look at kind of the main idea here from the notes for today. So the notes from today basically center around this theorem, theorem 8.1, which is known as the right triangle similarity theorem. This theorem says that if the altitude, so here's an important vocabulary word here, if the altitude is drawn to the hypotenuse of a right triangle, if I look at this picture here, here's my altitude, and this red altitude is being drawn to the hypotenuse of this large right triangle. If that happens, then the two triangles formed are similar to the original triangle and similar to each other. And so what you'll see here is that there's a total of 3 triangles. You have, and I'll try to do this with a highlighter, you have this large yellow triangle, you have this triangle here in green, and then you have this triangle here in purple. So you have a total of 3 right triangles. So this theorem says that the second you draw an altitude into the hypotenuse of a right triangle, you have now created 3 similar triangles, right? So we can say here that the large triangle in yellow, right, this is triangle ABD, would be similar to triangle CBA, which is the purple one. And that would be similar to triangle CAD, which would be the green one, right? And so you kind of looking at that similarity statement, it might be a little bit difficult to kind of see, where that statement is coming from. Because when we wrote these in the past, the order mattered, right? So let's go ahead and dive in and see how exactly is it that these 3 triangles are similar, right? And the way that we're going to do that is by following these 3 steps. So the very first thing we're going to want to do here is we're going to want to look at step number 1. Okay, it says in the large triangle ABD, you're going to mark the acute angles, angle D with 1 ring. So let's go ahead and do that. Let's go ahead and put 1 ring for angle D. And angle B will have 2 rings. So here is angle B with 2 rings. What we're going to do now is we're going to separate and draw out all 3 triangles with the rings that we have marked for angle D and angle B. So let's separate out all 3 triangles. I'm going to draw the first triangle as the big one, the large triangle as a whole. So the right angle here is located at A. So I'm going to draw my right angle. So this here is triangle DAB. And we marked this earlier with angle D having 1 ring. So I'm going to put 1 ring here. And angle B having 2 rings. Next, we're going to draw the triangle in red, the triangle here on the left, the medium triangle. If I look at this medium triangle, we see here that now we're looking at triangle DCA, where angle C has the right angle. And what you'll notice here is that in this red triangle, the red triangle contains angle D, right? And it was understood earlier that angle D was what we marked with 1 ring. So I'm going to put 1 ring there. And then angle B is the blue triangle here off to the right, the smallest triangle. If we draw this out here, then what we're looking at here is triangle ABC, where C has the right angle. And we marked angle B with 2 rings. Angle B is shared in the big triangle as it is in the small one, so this also is going to have 2 rings. So now let's take a look at how it is that these 3 triangles are similar. Okay, if you take a look here, one of the ways that we looked at proving 2 triangles are similar is by using the angle-angle similarity theorem. This says that if we have 2 pairs of congruent angles in 2 triangles, then the triangles must be similar. So let's look at the black triangle and the red triangle. Well, they both have an 90-degree angle here, so that takes care of one of the A's in angle-angle. And then we have a second pair of congruent angles, which would be the angles in green. So this would be similar by angle-angle. Okay, the same could be said here if I were to look at the black triangle and the blue triangle. So let's back that up here. So the black triangle and the blue triangle, if I look here, they both have a 90-degree angle. That takes care of one of the angles in angle-angle. And then they also have an angle shared with 2 rings, right? So that is the second pair of angles that are congruent. So the black triangle and the blue triangle are similar by angle-angle. And the black triangle and the red triangle are similar by angle-angle. So going back to what we said earlier in the notes, right? We said earlier that if 2 triangles are similar, let me back up here. If two triangles are similar, when the triangles are similar, the corresponding angles are congruent, meaning if I got a 40, then I have a 40 in the second triangle, 80, 80 in the second triangle. We're using that idea here with what we're looking at currently, right? If I have a 90-degree angle in the black triangle, I better have a 90 in the red triangle, which we do. If I have one ring, I better have one ring in the red triangle. Well, we've already determined that these are similar. So that must mean that if this black triangle has an angle marked with two rings, then the red triangle would also have an angle marked with two rings. And so now we're kind of building this out where all of the rings have been filled in for this triangle. Similarly here with the black and the blue triangle, right? We already said that the black and the blue triangle are similar. If I see here, the black triangle's already got the 90, the blue triangle's got the 90. If the black triangle has the double rings, then the blue triangle must have the double rings. And then lastly, if the black triangle has a single ring, then the blue triangle must have a single ring as well, making angle A be one ring. And so now we can kind of go ahead and fill out this and bring this full circle, right? Now I see that in each of these three triangles, I have a right angle, I have a single ring and a double ring, right? And that means that all of these in this case would be similar, right? The way that we would write this similarity statement now, if we want to kind of use the order that they started with earlier, let's start with triangle ABD. Triangle ABD here would be similar to, well, let's take a look at how they started. Triangle ABD, the order matters here. A is the right angle, B is the double ring. Okay, so they're going right angle to double ring. That would be similar to right angle to double ring would be CAD. So this would be triangle CAD. And then that would be similar to, again, we're starting with that same order, right? ABD was A is the right angle, B is double ring. So right angle to double ring, right angle to double ring would be CBA. And so now hopefully that similarity statement that they wrote above earlier kind of makes a little bit more sense. It's just kind of going in a different order. So triangle ABD is similar to, what I mean by different order is the green highlighted one is the second triangle that we wrote. But how that similarity statement kind of comes into play is by using these rings. All right. So let's get into kind of what it is that we're actually going to be asking you guys to do now. And before we jump into that, let's just kind of review here and understand that anytime an altitude is drawn to the hypotenuse of a right triangle, it will produce three similar triangles. So again, anytime that an altitude drawn to the hypotenuse of a right triangle, then it's going to create three similar triangles. So let's go ahead and look at how is it that we're actually going to solve these kind of problems. So example 2 says solve for x, right? What we're going to do is basically more or less use the same idea that we had earlier for separating out the three triangles with the rings and everything, all right? So if I were to look here, following those same steps, we got a altitude drawn to the hypotenuse of this right triangle. My altitude here is represented by QS. When this happens, this means that it's going to basically create a total of three similar triangles. And so let's take a look at these three similar triangles in question. And before we start, we're going to look at the large triangle as a whole, triangle PSR. Triangle PSR is going to have acute angles P and R. I'm going to label that with one ring for angle P and two rings for angle R. So what we'll do now is we'll separate out all three triangles. Here is triangle PSR, where S has a 90-degree angle, P has one ring, R has two rings. If I look at, let's kind of use the same colors here. If I look at the next one here, if I look at the red triangle here, the red triangle would essentially look like this, where this would be triangle PQS, and P has one ring. That would mean that Q here is labeled as the 90-degree angle. That means that S would have to be the one that is two rings from the conversation that we had earlier. And then lastly, we have this right triangle here in blue. Right triangle here in blue. We're looking at triangle Q with the right angle, R with the double rings, and then S means that it would have one ring. So as we look at this now we can go ahead and start labeling what we know for the current side lengths, right? If I look at the black triangle, the large triangle as a whole, we're looking at anything that we know about the side lengths. Well, I see here that S to R is X. So S to R, I can label this as X. I also see that from P to R, it's actually broken up into two pieces, 12 and 2. If I combine those, we get 14. So P to R is 14. And then I don't know anything else about the large black triangle. So look at the red triangle. The red triangle, anything that we know that from P to Q, it's 12. So PQ is 12. And I don't know this altitude here. And I don't know this side here for the red triangle. So that's all we know for the red one. The blue triangle, now we can see here that this bottom side is a length of 2. And here we have a length of x, right? And so now we've gone ahead and pretty much labeled everything, right? We've taken apart all three triangles. What we're going to do now is we're going to highlight our corresponding sides, right? So if I look at these three triangles, then we understand that yes, the corresponding angles are congruent, but now this means that the corresponding sides are proportional, and we can use that to solve for missing side lengths. So for example, if I were to look at this side here labeled as X, I see that that side is created by the right angle and the double ring. So that would correspond to right angle and double ring in the second triangle, and right angle to double ring in the blue triangle, right? So in yellow, these are my corresponding side lengths in all three triangles. Next, we can do the same thing here. If I look at PS, I know we don't know what it is, but let's just go ahead and highlight it. PS represents one of the legs of this right triangle. This is from the single ring to right angle. Single ring to right angle would correspond here. Single ring to right angle would be corresponding here. And then lastly, we can take a look here at from P to R. From P to R, this represents your hypotenuse, right? This is single ring to double ring. Single ring to double ring is your hypotenuse here. Single ring to double ring. And so what this basically does for us now is this basically color codes all of our corresponding sides. And we can use this color coding to start setting up our proportion. If we take a look here, they want you to find x, right? If they want you to find x, then we have to be working with a triangle that has the x, right? So if I were to take a look at the triangle that we started with, the big one, okay, I see here that I know this side length of 14. So let's see if we can set up a ratio with 14, right? 14 would correspond to the red triangle, but I don't know what it is. So that's not helpful. So let's maybe try using the last triangle, the blue one, right? 14 corresponds to x, so I can write a ratio of 14 over x, right? In other words, but basically what we're doing is, well, we're doing green over green. That would then be equal to, well, now if I want to find x, right, I'm looking at yellow here. Yellow would correspond to, I'm using the last triangle here, so x would correspond to 2 in this case, where this would be yellow over yellow. Similar to kind of what we did earlier in this year whenever we're solving these similar triangles, right? And so what you'll notice here now is that we have an equation set up where we can now cross multiply to solve for x. Now, if we're going to cross multiply and solve for x, then if we multiply our diagonals, x times x gives you x squared. 14 times 2 gives you 28. So we're left with the following equation after we cross multiply. X squared is equal to 28. If I want to solve for x, then we square root to cancel out the exponent of 2, leaving you with x is equal to the square root of 28. Which you'll realize that the square root of 28 actually simplifies. This could be broken down into 2 times 14, 2's prime, and then we can break this down into 2 times 7. Or 2's prime, and then we have the 7. So the 28 is basically going to become 2 times 2 times 7. And we see here that I got a pair of 2's, so 1, 2 comes out, and we're left with a square root of 7. So our answer here ends up becoming x is equal to 2 square root of 7 in simplest form, right? And so that is pretty much how we're going to work out these problems, right? The steps to kind of just go over one more time is you're going to put a single ring and a double ring in the acute angles of the large triangle. And then from there, you're going to separate out all three triangles. After you separate all three triangles, put in all your rings and color code and highlight your corresponding sides, right? Doing this after labeling will kind of make setting up the equation become a little bit more clear, right? And this is going to be more comfortable with the more problems that we practice. So let's look at one more, okay? If I look at the next problem here, this section of the notes goes over a shortcut to the method that we just looked at for solving these problems. These shortcuts will be gone. We'll go over these shortcuts in a separate video, a separate short video. Okay. For right now, let's practice what we basically learned. It says example 3, find QS. If I want to find QS, the first thing I'm going to start with is I'm going to label my acute angles in the large triangle. The large triangle here is QPR. So I'm going to label this acute angle with 1 ring and this one here with 2 rings. So let's do that in a different color so it's a little bit more clear. See this in green. So one ring and then two rings here. So from there, what we're going to do is we're going to separate out all three triangles. So here's the large triangle here, where this is triangle P, Q, R, with the right angle here at Q. We marked the angle P with one ring and angle R with two rings. Next, I'm going to separate out the right triangle here. And we just color code it here. It's this right triangle right here. And this is triangle PSQ with angle S having the right angle. And we marked the angle P earlier with one ring. So one ring. That means that angle Q would have to have the double ring. And then lastly, we have the blue triangle, the one on the right. Okay. If we were to separate this out, then we're looking at triangle SQR. So we got triangle SQR with a right angle located at S. And we see here that the R has a double ring. That means that Q would have to have the single ring. And so now we can go ahead and start labeling all of the side lengths that we know, right? If I look at the large triangle, the black one as a whole, we know that from P to R, we know that that's 30, right? And shame on me here, I didn't even read the question here. It said find QS. If they wanted you to find QS, then we can label that as X, right? So that's what the question's asking you to find. QS, we should have started off by labeling that as X. So in the large triangle, the black one, the only thing that I know currently is that from P to R, it's 30. I don't really know anything else. If I look at the red triangle now, though, I see here that from P to S, it's 6. So that's 6. And S to Q, well, that's X. That's what we're asked to find. Then if I look at the blue triangle, okay, if I look from S to Q, I see that that's X. And then I don't see anything else currently labeled there. But if I look at SR, I see here that this piece PS and this piece SR together have to create 30, right? So working backwards here, if we were to do 30 minus 6, that would tell us that my missing piece here would have to be 24, right? So that the 6 and this piece can create the 30. So that would mean that S to R is 24, right? And so what I would recommend here before starting the problems and for separating them out is definitely fill out all the information that you possibly can. So now that we've got everything pretty much separated and all of our side lengths labeled, what we're going to go ahead and do is highlight our corresponding sides. So I see that my side here is single ring to right angle. I'm going to mark in yellow. Single ring to right angle. Single ring to right angle, right? I realize here that we didn't finish writing this guy. This was QS. QS is X. If I continue marking my corresponding sides here, then I'm seeing double ring to right angle in green, double ring to right angle in green, and then double ring to right angle in green. And then lastly here we have our hypotenuse from P to R would be single ring to double ring, single ring to double ring, single ring to double ring. Right? So the whole purpose of the highlighting is really just to get us to see what's corresponding and to help us kind of set up these equations now, right? So if we want to go ahead and start setting this up to solve for X, then what we're going to be working with is the red triangle and the blue triangle, right? If I'm looking at the red triangle and the blue triangle, then I want to find X, right? The first triangle is not going to help me. When you're doing these types of problems, you need to know at least two of the sides of any given triangle, right? So this is not very helpful. But if I look at the red and the blue triangle, I can set up a proportion here, right? If I want to set up a proportion, we know that we can do green over green. If we do that, what we're looking at here is X over 24 is equal to, well, I know this side length in yellow, so let's do yellow over yellow. That would be equal to, well, 6 over my yellow piece here is X, right? And so an interesting thing is going to happen here for these types of problems. What will end up happening essentially here is that anytime you're doing these types of problems with similar right triangles, you're going to see that a diagonal repeats. So for example, this is my diagonal that repeats. I have an X and an X. That's a good sign, right? If your diagonal repeats, that's a sign that you did this setup correctly, right? So now that we understand that we set this up correctly, then what we're going to do is we're going to cross multiply. If I cross multiply, we get X times X to get X squared. And then we get 6 times 24. And 6 times 24, I believe, is 144. And from here, we want to solve for X. So we're going to square root both sides. That square root cancels out the squared, leaving you with X is equal to the square root of 144 which would simply just be 12. And there's our answer, okay? X is equal to 12, right? But let's be kind of a little bit more specific and accurate here. They didn't ask me for X, they asked you to find QS. QS we happen to label as X, so we'll just say here that QS is equal to 12. Okay? So these problems kind of are a little bit of work, right? But separating out these three triangles kind of helps you kind of see the connection to what we've learned earlier on this school year to be able to set up our proportions and cross multiply to solve for these missing values, right? Let's practice with a more challenging one to finish off the notes here. Let's look at example 3 here, or I guess 4 in this case. So in this problem, it says find the value of X, Y, and Z. So they were nice enough to label X, Y, and Z in the picture. And one thing that I should have done in the last problem was label everything that I possibly can, right? And what I mean by that is this, right? If I look at this entire picture here, I got X, I got Y, I got Z labeled, but these two pieces, 9 and 3, together, that would technically create the entire length from G to K. That would be 12. So that's what I mean by saying, like, go ahead and label everything you possibly can, right? Aside from that, there's not much more that we can label here. So at this part, now we can go ahead and start doing our labeling in our step 1, right? Our labeling in our step 1 is going to tell us to put one ring at angle G and then two rings at angle K, right? If you do the one ring at K and the double ring at G, that's fine. Going to work out the same way. But for right now, let's go ahead and separate out our three triangles, right? Here's the first triangle, the big one. This is going to have a right angle. This is going to be triangle GHK. And we have a one single ring at G and a double ring at K. Next, I'm going to look at this triangle here on the left, where we'll look at this right here. And what you'll notice here is that there's no letter here. There's no letter here. So we're just going to put out our own letter there. Let's call this L. Just call it L. So that would make the triangle that I just drew here, this one, to clarify. That would be triangle GHL, where we have a single ring located for angle G. That means that the angle H would have to have a double ring. And then lastly, we're going to look at this blue triangle here. This blue triangle is going to be looking something like this, where this would be HLK, where this is a right angle, and then we have our double ring at K. The double ring at K would mean that angle H would have to have the single ring. And so now we'll go through that process of let's label all of our sides, right? If I look at G to H, that is labeled as Z. H to K is labeled as Y. And then G to K, which is the entire length of the hypotenuse, we found out earlier that that length would be 12. Next, let's take a look at the red triangle. In the red triangle, I know that the bottom side is Z. From G to H is Z. This piece right here from L to H is X. So that's X. And then G to L is 9. In the blue triangle now, we see that L to K is 3. L to H is also X. And then H to K is Y, right? So we got everything labeled here. Let's go through our highlighting here to see our corresponding sides. So single ring to right angle, single ring to right angle, single ring to right angle. These are my corresponding sides. Then we'll look at double ring to right angle, double ring to right angle, double ring to right angle. Those sides are corresponding. Lastly, we'll look at the hypotenuse, hypotenuse, hypotenuse. Single to double, single to double, single to double. Right? So we got all of our sides color coded here. Now we need to go ahead and get started with finding X, Y, and Z. So this looks really overwhelming to start with. I would recommend, just pick a variable. Pick X, Y, or Z to start with. I'm just going to go in order. I'm going to start with X. If I want to find X, I'm going to look for what triangles has X. If I look at this triangle here, I don't see the variable X in here, so that's not going to work. So that tells me that I'm probably working with these two triangles. If I'm working with these two triangles, then let's look at what we have here. If I want to set up a equation with X, then I see here that X is labeled in green. So I can do green over green. Well, green over green here would be X over 3 is equal to, well, now I need another side in this triangle, right? It wouldn't make much sense for us to pick the blue side, because if I were to pick the blue side, then I would have the variable Z, and that's going to become a lot more difficult to solve since I already have an X. So let's refrain from using the blue side Z. Let's use the yellow side 9, right? So in this case, let's do yellow over yellow. If we do yellow over yellow, we're looking at 9 over X. And what I said earlier was if you set this up correctly, you should see a diagonal that repeats. I see a diagonal that repeats and it's my x. So that's a green flag. You can go ahead and keep going. If we go ahead and keep going here, then let's take a look at what we get. We have to cross multiply. This would give us x squared is equal to 3 times 9 is 27. From here, you would square root. If I want to solve for x, square root both sides. We see here that these cancel. We're left with x is equal to the square root of 27 can actually be simplified. 27 can be broken down into 3 times 9. 3's prime. This can be broken down into 3 times 3. So this means that x is equal to the square root of 3 times 3 times 3, which gives us a pair of 3's here, letting us know that x is simply going to be equal to 3. 1, 3 comes out. And we're left with square root of 3 on the inside. So our answer for x would be 3 square root of 3. Okay. We're pretty much going to repeat the same process to find y and z, right? So if I want to find y, I'm going to look for a triangle that has the variable y, right? I see a triangle right here that has the variable y. And so if I look at this triangle here, then we're looking at the following side length here, green, right? Green here is y. So that means let's try green over green, right? If I do green over green with y, if I look at my two triangles that I get to choose from, well, that's an x, so I'm going to refrain from using that. Even though I know what x is, I'm just going to go ahead and choose to deal with the last triangle. So I'm dealing with these two triangles, the first one and the last one, to do my green over green. Green over green here would become y over 3. Y over 3 would be equal to, well, now I need another side in this triangle to set up a ratio of. Well, I'm not going to pick z because I already have y. That's going to introduce a new variable, make things more complicated. So let's pick the blue side. Okay, let's do the side of length of 12. So let's do blue over blue. Blue over blue here would become 12 over y. And then before you kind of go ahead and start cross multiplying, check to see, do you have a diagonal that repeats? And you do. My diagonal that repeats is the y's. So y times y would give me y squared. And then 3 times 12 would give me 36. If we cross multiply and we get that equation, all that's left for us to do is solve for y. If we solve for y, we want to do this by square rooting. So if I square root both sides, then the squared cancels, leaving you with y is equal to, the square root of 36 is just 6. So there's our answer. Okay, we got x, we got y. Last thing for us to find is z in this case. So if I want to find z, I'm going to look for my triangles to see which one has z. If I see the last one here, there is no z here, so probably not going to be super helpful here. But I do see a z here in this triangle and in this one. So if we take a look here at setting up a proportion, well, if I look here, we have z is in yellow. So let's do yellow over yellow. Yellow over yellow would become z over 9. That would be equal to, I got to pick another side length here. I can choose the y now that I know what it is. I know it's 6, but let's just choose the blue one here. If I choose the blue one, then I'm doing blue over blue. In this case, we'd be working with 12 over, and the second triangle would be z. And so from here, now we cross multiply. Z times z is z squared. 9 times 12 is, actually, let's do some math here. What is that? 90. I think it's 108. I could be wrong. Let's double check with the calculator here. 9 times 12 is, nope, it is 108. Okay. And then from here, we square root. If I square root both sides, then we get z squared is equal to 108. Square rooting that gives us z is equal to the square root of 108, which I'm going to do off to the side here at the very, very right. The 108 can get broken down into 2 times 54. 54 can get broken down into 2 times 27. 27 gets broken down into 3 times 9. 9 is 3 and 3. So this square root of 108 will end up becoming 2 times 2 times 3 times 3 times 3. When I simplify here, I got a pair of 2's, so 1 comes out. Then I have a pair of 3's, so a 3 comes out. And then we're left with just a square root of 3. This ends up becoming, when we multiply the numbers in front, 2 times 3 is 6, so 6 root 3. So our square root of 108 simplified becomes 6 root 3. Okay, and so that represents our values for x, y, and z, and with that, we finish up example 4. Okay, so the key takeaway from today's notes is going through our steps. Whenever you see these problems, label everything you possibly can in the picture, right? So we started with the 9 plus 3 here to get the 12. After you've done that, go ahead and start with the large triangle. Label one of the acute angles with one ring, the other with double rings, and then separate out all three triangles. Color code your corresponding sides, and from there you can cross multiply to solve for any missing information. And then the last kind of reminder here is if you set your proportions up correctly, you should see a geometric mean. And what this means is that one diagonal repeats. All right. And so that'll be the end of the video. I know that we skipped a section in the notes here, specifically this section right here. There's going to be a part 2 to today's video that goes over these shortcuts and how these shortcuts can get you to the equations and set those up a little bit faster. All right. But if you have any questions or you're struggling, found something confusing for the notes, please make sure that you're reaching out to your teacher and scheduling a time to come in for tutorials.